Thank you. Let me start by recalling kind of the overall picture and where I am trying to get in this last 15 minutes or whatever we have. So I began by referring to a couple of theorems which I aimed to explain something about the arguments toward. And theorem A concerned geodesic flow for a complete negatively curved non-compact manifold. And theorem B concerned the Sinai billiard map. And in both cases, the goal is to prove that there is a unique measure of maximal entropy. And in both cases, this was already known under certain conditions, and we present some ideas which lead to a proof in a little bit greater generality. So the goal is unique MME. And I made some argument in the first couple of talks that a major component of the progress towards this goal should be getting uniform bounds. So we want to say that lambda n is bounded above and below by constant multiples of e to the nh. Of course, lambda n must be defined and interpreted appropriately. And in the case of a shift space with specification, well, just a shift space, I guess, on a finite alphabet, this was just the number of words of length n in the language. And if there is a specification property, then the thing which lets you deduce this fact is that the quantity lambda n is submultiplicative and is approximately supermultiplicative. So these were kind of the main ideas. And in order to say something about the settings of theorems A and B, one needs to establish this inequality in a more general setting, in the settings of the theorems, after making appropriate definitions. So last time I gave some idea of what specification and expansivity should mean in the setting of theorem A or for non-compact flows more generally. Today, I need to explain what is meant by this three-letter acronym SPR, which I put up and which has by now appeared in several other talks, but there are multiple ways of defining it, so I should explain exactly what I mean by it and how it relates to other possible definitions. I should mention, since I will not go into it in too much detail, that although I am describing theorem A in the context of the measure of maximal entropy, there are also versions of it for non-zero potential functions, subject to some regularity condition. And although I am only talking, I only said anything about Riemannian manifolds, there's also an application of our general result to cat-1 spaces. So you don't actually, it's not actually essential that you have the smooth structure. Rather, what is important is the framework of specification and expansivity in the non-compact setting. So, to that end, let X be a complete separable metric space in which every closed ball is compact and let ft be a continuous flow. Last time, I introduced the family of reference sets, so compact subsets with non-empty interior. And in order to start playing the game of having these counting estimates, we needed the appropriate definition of lambda n. Well, it's a flow, so it should be lambda t. And this was given in terms of these sets at. So you have your reference set, and then you consider all points whose orbit segment of length t returns to A at the end. And maybe it comes through in the middle, maybe it doesn't. So lambda t is the maximal cardinality. There's a scale epsilon and there's a set A. So this is the maximal cardinality of a set E. Let me write it this way. Let me write it this way. A T epsilon. There. But I'm done correcting myself now. So A T T epsilon. And now the game should be to use the specification property, which for a non-compact flow, we define in terms of orbit segments that are making such returns. So specification means that you can glue such things together, and it has this formulation that for every rho, there exists a tau, and rho here is the scale at which you wish to shadow, and tau is the time that it takes to transition from one orbit segment to the next. And tau is allowed to depend on both A and rho. So this is a crucial difference from the compact case, that your transition time is allowed to depend on where the orbit starts and ends. Similarly with expansivity, there should exist some scale epsilon at which everything is expansive, and I defined this in terms of some coherent family of metrics, which I don't want to get back into right now because there are other things to say. But I do want to point out that this scale is also allowed to depend on the reference set A. So the point is that if an orbit returns infinitely often to some set A, then when you look at it in that set, you have the expansivity property at this scale. But as your set A gets larger, that scale could go to 0, because you may have some manifold with cusps, you may have the expansivity scale decay. And under these conditions, I formulated a variational principle for certain quantity. So if we take the exponential growth rate of this, we get the entropy with respect to the reference set A. And using the expansivity property, it is possible to prove that HA is equal to that HA at a scale epsilon is in fact equal to the topological entropy, which a priori is defined as the supremum over all reference sets of the entropy at all finite scales. I guess in order to say that it doesn't depend on the reference set, then we need specification too. So this is kind of a consequence of both of these. This is an essential step in the kind of approach we take, that you are able to fix once and for all a single reference set, and once and for all a single scale, which may depend on that reference set, and you work at this scale and you are guaranteed to see all of the entropy in the system, or more generally, all of the pressure. So this is the setup for the main story. And then we would like to prove some uniform bound like this. So we want to prove that the partition sums here, lambda t, that these admit some uniform bounds such as the ones there. Now, the usual specification argument involves some kind of sub and supermultiplicativity. And the second half of this is completely fine in our setting, because if you take a bunch of orbit segments that start and end in A, and a bunch of orbit segments that start and end in A, you can use the specification property to glue them together, and you get longer orbit segments, and that's exactly how this upper bound is produced. So that one is fine. This one is more troublesome. And the issue is the following. When we look at just a shift space on a finite alphabet and we are counting all the words, a word of length n plus k must start with a word of length n and end with a word of length k. But an orbit segment of length, say, t1 plus t2, which begins and ends in A, does not have to return to A at time t1 in the middle. So there is no analogous submultiplicativity property for these quantities. And this makes life much harder. And this is why we need a strong positive recurrence condition. I haven't said what it is yet, so I should do that now. Well, if our goal is to have submultiplicativity in some sense, and we only have submultiplicativity when we return to A, then we should have some property that guarantees we return to A often enough. And if we want to guarantee we return to A often enough on most trajectories, then we should say something about the trajectories that do not return to A. To that end, if you fix a reference set A, a time t, and a scale L, we consider the following set of points. Points x, which begin within a distance L of the reference set A, and which after time t also land within a distance L of the set A, but between time 0 and t, they never enter the set A itself. So you can do whatever you like, but this is forbidden. And we want to control the growth of such things. And this leads to the strong positive recurrence condition. The terminology, we borrow it from Omri, who used it for countable state Markov shift thermodynamic formalism, and I believe he borrowed it from the theory of random walks. And in that setting, it's been studied for quite some time. And of course, now you hear it in various places. We talk about entropy at infinity. You've seen this in various talks. So what strong positive recurrence means for me is the following. Well, I need a definition, and then I will say what it is. So let me define the following quantity. What did I call it? H star A subscript L. Hopefully you can guess what this quantity ought to be based on the other notation in the picture, but well, there is one minor subtlety, so I better write it down. We'll take the growth rate of the partition sums associated to these sets of non-returning points. You take that at some scale zeta and then you send the scale zeta to 0, and you take the limit of these entropies. What, you want exponential growth, not just linear? Yes, 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 you are, of course, right? Thank you, Dan. This is why you need co-authors. They save you from many silly mistakes. All right, much better. So, the definition of strong positive recurrence that we use is that there exists some L such that this growth rate is strictly smaller than the entropy. Now, if you remember the annoying little details of how this quantity, this property of strong positive recurrence was defined in various other talks, you may notice that there is some difference. Maybe it appeared this way or something analogous to this at some point. But we are considering orbit segments which are not allowed to return to A at all. It's completely forbidden. However, in various places, you may see the entropy at infinity defined in a mildly different way, where you fix some small threshold, call it gamma. And you consider orbit segments which can spend some time in A, but only a small time. They can spend, say, at most gamma of their length in A. And there is a relationship between the two. So a important proposition for our proof is the following. At the bottom of this board, I've drawn a perhaps incomprehensible picture, which plays an important role in our counting arguments. So let me try to explain it. Consider some trajectory like this, which begins and ends in A. The yellow skinny rectangles here, these denote the set of times between 0 and capital T, at which the trajectory is actually inside the set A. So it starts in A, it ends in A, and if you look at this trajectory, there are two intervals in between where it comes back through A for a while. And so these are here and here. Now I want to take each of these intervals. I'm going to fix some scale, some time scale capital delta. You should imagine that capital delta is very large, despite the picture. The issue is that capital T is even more very large. So I take the set of times at which my trajectory lies inside A, and I expand it on either side of every interval by a width delta. And then I look at what's left. And what's left is these red squiggly intervals. And WT delta x is the total length of these red squiggly intervals. Red squiggly interval is probably not a sophisticated enough term to go in a paper. And so we refer to these as wandering intervals. Yes? Yes, exactly. Well, I guess in the picture above, I probably should have changed the color of the curve when it is outside A. And similarly elsewhere. Yes, thank you. Yeah, so the yellow intervals are only the points where it is inside A. So we have these wandering intervals. The total length of them is this quantity W. So W is somehow the total wandering time. It's not simply the time you spend outside A, but it's the time that you spend, spending a long time without visiting home. the main proposition driving a lot of these estimates is the following. Let us consider the following set of bad points. So these are bad orbit segments of length t. These are orbit segments which start and end in A, but which spend a substantial portion of their time inside a wandering interval. And substantial here means 1/3. So it's points for which at least 1/3 of your time is spent doing something like that. And now the proposition, which is one of the central pieces of the counting argument in our paper, is that if you have the strong positive recurrence property, then these bad orbit segments cannot carry full entropy. That is, if you make your window large enough, remember capital delta is the size of the window, and so any excursion away from home that is less than delta in time does not count as a wandering interval. You came home for Christmas, so everything is fine. Then, as long as delta is large enough, the exponential growth rate, I'm remembering the logarithm this time, associated to these bad orbit segments is, once again, strictly smaller than the topological entropy. And this is much more in the spirit of the strong positive recurrence in the sense of entropy at infinity that we saw in, for example, the talk of Annabelle Veloso. Also, Barbara Shapira has some version of this. I should mention that, so there's this paper by Barbara and Anna Florio and Anne Vaughn. They have some argument which is essentially exactly this proposition, and it involves what they call Gurevich entropy and at infinity and chord entropy at infinity. And the result is essentially this one, assuming I have understood it correctly. If I'm not, I'm sure that I can learn it better from Barbara later. But this idea is somehow something you have to do in order to play this game in this setting. Yes? This is, I am not going to commit to this being the only place. I'm pretty sure we need it in some other places as well, although I would have to look at the paper to remind myself of exactly where. I mean, no, I don't think so. Because probably we need the original version of strong positive recurrence when we deal with integrability of the inducing times later on, would be my guess. There is a part of the argument that I will not subject anyone in this room to, myself included, that involves inducing maps and graded and sliced adapted partitions and a uniformly integrable inducing times. And I believe that for that part, we probably need the original version, I think. So. Don't throw the wrapper out just yet. You might need it later. Okay. Hey, I suppose if you know that these grow more slowly, then of course those must grow. Yeah. Because somehow this is the set of things which do not return is a subset of the set of things which do not return often. So, yeah. So, probably either one is okay to use, but you certainly need one. You need to keep these around. So the goal after this is to go on and get these uniform counting bounds. And well, let me maybe say just a couple words about how one proves this proposition, because I think it's kind of a sort of argument that shows up in various places, at least in the stuff we have to do with this. So what is the idea behind the proof of this proposition for us? The way that we prove it, you sort of, for each such orbit segment, you look at where the wandering intervals happen. And you look at the starts and ends of those wandering intervals. And you call that the wandering schedule. And so, if you consider all of the good orbit segments of length t, where good, set a low bar for being good, it just means that you are not bad. This is partitioned by the wandering schedule associated to the orbit segment. Where by wandering schedule, I mean when these wandering orbits begin and end. And then the second step is to list all the schedules. Or I should probably say enumerate all the schedules, because I don't really want to list all of them, but you do want some kind of count. But enumerate is too long a word to fit in the board space I had left, so we'll settle for list. Now, once you have this, you can then make the following argument. To get the uniform counting bounds that we have set as our heart's desire, you observe that everything in ATG returns often enough. This is, of course, incredibly vague. But somehow the idea is that you want to say that some orbit segment like this has many returns into A, so many of those returns must be separated by some fixed distance some fixed amount of time that you are interested in. And then once enough of those are separated by a certain fixed amount of time, you can run a submultiplicativity type argument for that amount of time. And to go from hand waving to something intelligible would, I think, take us too far away from the goal, which is to just explain the rest of the strategy here and then to say something about billiards, since I did mention those in that first talk. So from this point on, once you have the uniform counting bounds, you kind of play the game exactly as you expect to, dealing with any difficulties which come up on the way. So the first part is not so bad. You build a measure using the usual Mizarevich construction of an MME, except that because you have your counting bounds for orbit segments that begin and end in A, you must use exactly such segments. And because you are in a non-compact space, you cannot pass to a limiting subsequence of the space of measure, of the sequence of measures, unless you know that it satisfies some tightness property. So this is a key step. You use the uniform counting bounds coming from strong positive recurrence to prove that the sequence of equidistributed measures in the Mizarevich construction is tight in the sense that for every delta greater than 0, there exists a compact set such that the complement of this set has measure less than delta for all sufficiently large t. And this is enough to guarantee that your sequence of that your family of measures actually admits a subsequence which converges to an invariant probability measure, and that is your candidate MME. Now, once you've built the candidate MME, there are two remaining things to do. You must prove that it is an MME, and then you must prove that it is the unique one. Along the way, it is helpful to have Gibbs bounds. And these follow exactly as in Bowen's original argument, because you have the counting bounds and you're using this Mizurevich construction, so it's pretty straightforward to get the Gibbs bounds. However, Gibbs bounds, we formulated in terms of Bowen balls. Here, they only work for Bowen balls associated to orbit segments which start and end in T. Sorry, which start and end in A. And if you consider orbit segments starting and ending in a larger reference set, then the constants in your Gibbs bounds will be worse. And this is unavoidable. At the moment, we only have these Gibbs bounds at the scale that the expansivity happens, at the scale that you make the construction at. At the end of the day, once we have proved uniqueness, you'll be able to say that these Gibbs bounds hold for Bowen balls of any scale. So arbitrarily small scale, you still have the Gibbs bounds and you still have a very fine control of what this measure looks like. But then you must prove that it is an equilibrium state. And by equilibrium state, I of course mean MME, because I am trying to simplify my life. And already at this point, there is a need to do something unpleasant. Nothing before was unpleasant, I promise. So the idea is that we define some sequence of inducing times on some reference set, and I have written A+. A+ is a slightly enlarged reference set, never mind what, and then some return map from A+ to itself. And if we build these partitions in an appropriate way, you can use them and this return map to prove that the measure you built is an MME. And these partitions should have some kind of adapted property they should be adapted to Bowen balls, but this is the part I promised I wouldn't talk to you about, because it gets unpleasant, and the next part also gets messier, which is then when you want to show uniqueness. Well, then you need to really think about what the term adapted partition ought to mean in a setting like this. And I will just say that there is some version of sliced adapted partition, some version of graded adapted partition, and some kind of hybrid between the two, and you have to work with this hybrid in a way that eventually allows you to run these arguments using this induced map. And because I said the words induced map, and I know the work many of you have done, I should emphasize that this induced map is absolutely not Markov. There's nothing Gibbs Markov about this. So things become much messier as a result of that, as I expect you can believe. And since I gave these talks the title, a slightly larger reference set. Never mind exactly what. So, because it contains the set A, but I mean, it contains good things, bad things, whatever. Yeah. And then, so this return time may become arbitrarily large. You have to make some argument that these return times are uniformly integrable with respect to the measure you are interested in, et cetera, et cetera, et cetera. As I said, it is unpleasant. And because I gave these talks the title of Keeping Things Bounded, I want to keep everything bounded, including the talk. And so I want to focus on this idea for the last 10 minutes or so in the setting of the Sinai billiard map. So I want to change settings now. Yes?
So in the second step, whenever you do the inducing, for the induced system, you're no longer looking at that and it is a also movement over on the induced.
So we make some argument that in fact, if I remember correctly, I believe the argument we make is that we use this induced map to build some partition on A+, which is generating for the original time one map in the sense that it sees all of the entropy. So that then you just work with the original time one map. But you need the induced map to build the correct partition. That's I told you it was unpleasant. Okay, so let me say something about billiards. So this is what I mean by a Sinai billiard. This is the setting of theorem B. I mean a flat torus with some finite number of disjoint, strictly convex scatterers removed. So let's say I call these D1 and D2. And then the remaining part of the table is capital omega. This is the billiard table. The billiard map is the map we obtain by looking at collisions. So it is the Poincare section of the billiard flow on the boundary of the unit tangent bundle to the table. And we can describe the phase space of this map as a bunch of cylinders. So each collision is recorded by the position, which tends to get denoted Q, and the angle, which tends to get denoted phi, the angle it makes with the outgoing normal. And there is a natural invariant family of cones here, which Mark referred to in his talk. But before I talk about those, I should say something about the coding. So this map is, of course, discontinuous, because if I have this trajectory, it hits D2 next, whereas if I have this trajectory, which is not so dissimilar from it, it hits D1 next. So there is a discontinuity. So if I look at the discontinuity curves of T, I believe they look something like this. There are rather more of them, but hopefully the schematic is enough to give some idea. And if I look at the discontinuity curves of T inverse, they look something like this. So what I am doing here is I am partitioning the phase space. So if we call this M1, then the phase space is the union of finitely many cylinders corresponding to the scatterers. And P is the partition of M into maximal connected domains of continuity for both the billiard map and its inverse. So it is a finite partition, and then X will be the coding space associated to it. So You index this finite set of, you index the members of this finite partition. Given a point, given a trajectory, you just keep track of which sequence of sets it lands in, and this gives you a coding of the trajectory. And then you take the closure of the set of possible codings. You now have a two-sided shift space. It's not an SFT. I can't actually give you a quick proof that it's not an SFT, but I mean, come on. There's no reason for it to be an SFT. And because I have spent rather more time than is healthy thinking about specification properties, I also spent rather more time than is healthy trying to apply them to this example, but we never were able to. However, it turns out there's another way. And this is kind of why I want to bring up this example, because it illustrates different ways that this idea appears. So let's look at this coding space, and let's recall something that I said in the first talk. I take my two-sided shift space, and I consider the set of all forward infinite sequences which appear, and set of all backward infinite sequences which appear. So these are one-sided shift spaces. And then I consider the Hausdorff measures associated to the Hausdorff dimension on these one-sided shifts. And this goes back to one of the characterizations of the 1/2 Bernoulli measure from the very beginning, that these are the ones with a very nice scaling property. And then I define some measure, let me call it mu tilde, which is the direct product of these. Well, where does the product live? It lives on the product of the shift spaces. So this is a measure on this product. And if X were an SFT, then you could define this on each one cylinder, and then this product would actually be the shift space X, and all would be well, and this would be your MME. But X is not an SFT. So not every past can be joined to every future. And so this, in fact, is probably something bigger. So the goal is to do the following. First, prove that each of m plus minus is positive and finite. Which will follow immediately if one can prove these uniform counting bounds for the language of the shift. And then, to prove that this measure mu tilde actually gives positive weight to the shift space that codes the billiard. So that even though there are some things in X tilde which are not allowed, there are enough things which are allowed that you have your actual MME. And then once you can do this, the restriction is the MME, at least up to normalization. And I should mention in passing that this is, of course, in many ways very similar to what you do in a Patterson-Sullivan construction, right? You look at these boundary at infinity as the set of possible pasts. You also look at it as the set of possible futures. You put a measure on both of those, you take the product of the measures, and you get the thing you are looking for. It's the same here. Now, I don't really know what the connection is between the Hausdorff measure construction and the usual way of constructing Patterson-Sullivan measures, and that's something I would love to understand. But this is the general strategy, and in the last handful of minutes, I will say something about how it's carried out. So the key proposition is the following. I need to bring this back down. Okay. In the phase space for the billiard system, there are invariant cone families, which, as I said, Mark mentioned in his talk. So there's some unstable cone, and there is some stable cone. And I am going to be interested in curves which are tangent to the unstable cone. So by this I mean a U-curve. So given a U-curve V, it may be short, it may be long. What I would like to know is if I have a point which is constrained to lie on that U-curve, what possible futures can it have? Which words can it appear in the cylinder of? So each U-curve defines some set, let's call it LNV, the set of possible words which can follow. So then let's let lambda NV be the cardinality of this. And here's the thing that makes everything work. Here's the proposition. So for SPR, there was that kind of key proposition that you have to work to get, but then once you have it, things kind of go through. Here, the key thing is the following. For every delta greater than 0, there exists some constant greater than 0, such that if the length of the U-curve V is at least delta, then the number of words which can follow that U-curve is this positive proportion of the total number of words. And I should hasten to point out that we did not come up with the original proof of this. If you look in this paper by Vaughn and Mark, the paper of Baladi and Diemers, there is this, I don't remember if they actually formulate a proposition which says exactly this, because the setting in which they are working requires them to also deal with various potential functions and estimates that we don't need to deal with. But certainly they have this result. And so in our paper, we include a proof of it that gets rid of all of the complicated function-related estimates. But once you can prove this, then it becomes not so bad to get the kind of sub-multiplicativity, super-multiplicativity estimates that you need in order to get the uniform counting bound. And the thing which makes it all run is the possibility of working at the level of individual leaves. And since time is short, I will just say one thing about how this is proved. Which is, you can use various growth-fragmentation lemmas. If you look at what happens to this U-curve as you iterate it, it expands. So it gets longer because it is in the unstable cone, but it can also fragment into different pieces because it crosses these discontinuity curves, these singularity curves. And the point is that somehow the growth beats the fragmentation, so that when you look at the average lengths of the iterates, and maybe I can write at least that much down, that the average length is at least some constant once you go for long enough. And this is kind of the thing that makes everything run then. So to go any further would take more than the negative amount of time I have. So I stop here and thank you for following me the whole time.